Okay, so welcome everyone to the third seminar of the spring edition of the Spotlight Seminars on AI, which is organized by the Italian Association of Artificial Intelligence and in collaboration with the Society for the Study of Artificial Intelligence and Simulation of Behavior, AISB, represented by Floriana Grasso here. Today our speaker is Guy van der Broek. Is going to talk about a very important aspect of current AI research, and I will give the floor to Luciano for introducing our speaker.
Okay, thank you very much, Antonio. So it's really a great pleasure to introduce an outstanding speaker like Guy van der Broek. I don't know if I pronounced very well. Anyway, he is associate professor at UCLA and also Samueli Fellow, which means like a junior chair, I think, something like this, in computer science. He directed the STAR AI Lab, that stands for Statistical Relational Artificial Intelligence Laboratory. His research interests are in machine learning and knowledge representation, and of course, the integration of the two, reasoning in artificial intelligence in general. His paper has been recognized with a lot of awards in many conferences, like AAAI, or Uncertainty in Artificial Intelligence, KR, and also Guy received the NSF Career Award in SLAN and the SLAN Fellowship, and the Ichigai Computer and Thought Award. So no other time before giving the floor to Guy van der Broek, and thank you for accepting, and the stage is yours.
All right, thanks so much for inviting me to give this talk. I hope you can hear me well. And yeah, so what I wanted to talk about today is this topic of symbolic reasoning for large language models, because of course, large language models are taking over the world. Yet in AI, we have a lot of knowledge about how to reason about symbols and to do good old-fashioned AI. And so, what is there actually that is kind of using both of these ideas in a fruitful way? This all has to do with getting these learned models to do reasoning. And first, I would like to show you something that may actually scare you a little bit in thinking that the current way we get these models to do reasoning is actually achieving our goals. And so this will be the paradox of learning to reason from data. And the conclusion here will be that maybe end-to-end training to achieve reasoning is probably not going to happen in the way that you exactly want it to happen. And so then I'll try to offer two possible technical solutions to this problem, where we inject symbolic reasoning algorithms at generation time and at training time. And so here we'll make heavy use of logic and probabilistic reasoning at the same time as using a deep learning model to represent the distributions we have. Okay, so let's get started. The paradox of learning to reason. And so here we were motivated by all these benchmarks. You can look at an example like this from the Clutter data set that is supposed to be testing whether your language model is doing reasoning. And so what's happening here is you get a little story and then a question about this story, and you have to figure out that Carol is the grandmother of Justin, okay? And so now there's really two options of what's going on here. One option is that through this input magic, somehow the right output is being produced in some way that is not really understandable by us, or maybe the algorithm for logical reasoning has been learned from this text. The model has learned to extract basic facts from the premise of the story, and then was able to somehow learn to chain together these steps of reasoning, similar to how you would prove a mathematical theorem, right? And both of these are useful ways of doing reasoning. Especially the first one can make you a lot of money if you want to figure out if customers like your product from the reviews and so on. But if you are talking, let's say, to a AI medical health professional, maybe you would like something that has some form of logical reasoning in its way that it achieves its outcome. Okay, so we'll try to distinguish between these two scenarios. And the way that we'll try to do this is by setting up the simplest possible reasoning problem, right? So our goal here is not to make it very difficult and to really impress you with how complicated of a reasoning task an LLM can solve. No, our goal here is to just make it as easy as possible to learn how to do reasoning and then figure out how is this reasoning achieved, okay? And so the simplest thing we could think of was a very simple fragment of propositional logic with a small number of terms in the vocabulary, a bounded number of rules, bounded reasoning depth, where essentially you're given these little puzzles. Alice is blah and blah. There's some rules. If Alice is this and that, then the other must follow. And then the question is, does something follow? Okay, so very simple kind of implication rules. There's no language variance. These examples, they all look the same. All of the puzzles you'll ever be given look like this. It's completely templated. It's completely self-contained. You have to know nothing about the real world. You don't have to understand that fast is faster than slow or whatever. You know, these are not, that doesn't matter. These are just properties of Alice. And everything's purely symbolic. And so there's no reason why you wouldn't be able to learn how to solve this, because also there's an efficient algorithm for it. This is just definite clause logic. And in linear time, you can solve all of these problems efficiently, okay? All right, so now we have a very simple type of logic puzzle. And what we'll do is we'll generate millions upon millions of examples of this form. We'll train a transformer, and then the transformer will, in the end, say true or false as the answer, and that it hopefully will learn how to do reasoning, okay? Okay, so we've defined the type of like logic puzzle we would like to train here, and you know, in the end, it looks like this in natural language. And now we have to generate our data set, okay? And to explain how we generate the data set, so this might seem like a little bit of technical detail here, but actually it will turn out to be quite important. The way that we generate the data set is like we think of these puzzles as being little graphs where A, B, and C are the facts. A is false, B and C are true. D, E, and F are other variables, and they may be derived to be true or unknown or false. And the edges here are clauses that say if B and C is true, then F must follow. If A and B are true, then D must follow, but A is false, so D doesn't follow from that rule, okay? So we have to generate problem instances that look like this, essentially little graphs with edges and labels for true and false that are consistent with those edges. So one student says, okay, let me try to generate first all of the facts. I decide A must be false, B and C are true. And then I also generate some random rules. And then I just open my Russell and Norvig textbook. I look at the algorithm for forward chaining or whatever. And I actually figure out that from the rules and the facts, E and F must follow. So now I have this example, and it can go either in my training set or my test set. It's been randomly generated, okay? Now this student generates millions and millions of train and test examples this way and trains the transformer. And indeed, as you expect, you get 100% accuracy almost, up to the hardest reasoning problems that need 6 steps of reasoning, you still get 95% accuracy in predicting whether something follows or not. All right, so great job. And so this is usually where the research trajectory ends, right? Now the PhD advisor is saying, okay, great job, student. Let's publish a paper together. Let's say that we learned how to solve this reasoning task. We get very impressive accuracies. Job well done. Another publication under our belt, okay? But now suppose that for some reason, I have another student who also would like to run this experiment. And this student makes a slightly different choice. So this student actually generates these random train and test instances by first assigning true or false to each variable in the story, and then randomly selects a bunch of rules that essentially explain why all the variables must be true or false, okay? So here, first you decide whether everything is true, and then you randomly select rules that are compatible with it. Now, this student also trains on their data set a transformer, and they get even better results. They get 100% accuracy up to reasoning depth 1, and still 99% accuracy for the hardest problems. Okay, so great. I guess we'll write another paper about having done an even better job. Okay, but our real question here is, has the transformer actually learned how to do reasoning, how to do logical reasoning from this data? Well, here's all the evidence that I want to present to you as the judge. And first piece of evidence is what I said 5 minutes ago, which is that this is the easiest type of reasoning problem you could think of. You have to know nothing about the real world, no common sense knowledge, no nothing. It's tractable. There's no reason why you wouldn't be able to learn this. Both of these students, we call them RP and LP, they cover the whole problem space. It's not like you train on multiplication of 5 digits and you test on multiplication of 7 digits. No, these instances, they all have the same support in their distribution. The model has 100% accuracy on the test set, and traditionally in machine learning, if you have test set accuracy that's very high, you conclude that you've learned to generalize and therefore you've learned the concept. And then maybe the most convincing evidence is that you could actually handcraft the parameters of the transformer to compute the correct reasoning function. So we have a theorem in this paper that says with a certain number of layers and tension heads and so on, you can actually just run the Russell and Norvig textbook algorithm to derive true or false here. Okay. And so it's not that the model doesn't have the capacity to learn this. The parameters are right there. We just have to find them during learning from the data. So surely, I hope you agree, under these conditions, the transformer has learned the ground truth reasoning function. Okay. And so now there's a paradox, and it's all in this table. If I take the model trained by the first student and I evaluate it on the test set of the second student, suddenly the performance drops from 95 to almost random guessing. Okay, so this model that the first student trained is somehow not able to solve the harder problems in the second student's test set. And even worse, the second student's model, which was really, really strong, completely tanks when it's tested on the first student's test set. And in particular, even for reasoning depth of 1, where the second student got 100% accuracy, it suddenly becomes 66% accuracy. And so this is where this should give you some pause, where if the transformer has learned to do reasoning in the kind of formal logical sense, then this should never happen. We should get 100% here everywhere. The algorithm from your AI textbook doesn't care what the distribution is over instances that you're running it on. It always gets the right answer. Okay. But then if the transformer has not learned how to do reasoning, then how on earth does it achieve this perfect distribution in distribution test accuracy? How is it able to solve all these unseen logic puzzles with 99% accuracy without actually learning how to do reasoning? Okay. And so this here is the apparent contradiction, the strange paradox that we find in this experiment. Well, of course, there's some explanation here, as there is for any paradox, and it has to do with statistical features. So, as you know from studying logic, there's basic properties of logic like the monotonicity of classical logic, monotonicity of entailment, that any rules can be added without, and this isn't going to disprove any fact. Okay, and so the more rules you're given, the more likely it is you can prove that something follows. And indeed, you actually see this in the distribution of the first student's data set, the second student's data set, and even some third differently generated data set, where every time the number of rules does tell you something about the probability that the label should be true. And the question is now, is our model that we've trained from data actually using this statistical feature, yes or no? And so what we did here is we took the first student's data set and we downsampled it. We made the distribution in all ways equal to the original one, except for the fact that now the number of rules no longer tells you anything about the label being true. Okay. And if you do this, then indeed you see that the performance starts to degrade quite a bit for the harder problem instances. And so this is some evidence that indeed the model is essentially picking up on this monotonicity of entailment as one of the reasons to guess what the right answer should be. Now you might say, okay, this is fine. We just need to remove all of these statistical features, right? Because once we do that, we'll have to learn the right algorithm. And now, unfortunately, there's many properties of logic, and many of them we don't understand. And there's the cross product of all their properties. And this is something we never really are able to do. Even running this downsampling experiment was very expensive. And what's really happening here is that if you're trying to learn a reasoning function, that reasoning function has some mathematical properties that will always be statistical features. And getting rid of them is essentially impossible. They're really inherent, and you cannot make the data clean. And so this is very different maybe from how you think about other types of shortcuts in machine learning, where sure, if you accidentally put snow in the background of every wolf instead of dog, you can get rid of that snow, but eventually you hope to maybe get the data to be clean. Well, it seems like for reasoning problems, because those shortcuts are really inherent to the concept itself that you're trying to learn, this is not really an option. Okay, so that brings me to the first set of conclusions for the talk. There is a difference between learning to do reasoning in the formal sense and learning to achieve high performance on these benchmarks using statistical features. And hopefully when you see tweets and reports in the news about reasoning, you can maybe contextualize a little bit these achievements by thinking of these statistical features that were there for this particular reasoning problem to get almost perfect accuracy without actually learning how to do anything. It's essentially the student having no idea what the algorithm is, but having being very clever about how the professor asks questions to be able to guess most of the answers right. I think we've all been there when we were studying, right? Where we had our own heuristics for guessing what the answer should be, even if we had no idea about the actual correctness of the solution. Okay, so be careful deploying AI in applications where this actually matters. Especially when people talk about deploying AI in high-stakes scenarios, I get very nervous. So whenever I give this talk, I get some frequently asked questions like, does it help to just have a bigger transformer, right? We ran this on rather small transformers because they were good enough to get 100% accuracy essentially on these benchmarks. I don't see how bigger transformers will help you here because we already got 100% test accuracy. And then sometimes you can get really philosophical and ask, will reasoning emerge somehow magically? We'll train on some random set of objectives, a very, very large model, and then it will suddenly turn into a human brain and whatever. I'm not sure. These are very philosophical questions I don't really wish to engage with very much. I'm not qualified. But maybe one perspective is that yes, a lot of human behavior is very predictable, and also the type of reasoning humans have to do might be very predictable and come from a distribution that is rather easy to capture. But then every once in a while, someone invents calculus or jazz music, and then the distribution shifts. And so in that sense, it is good to have a reasoning capability that's very robust against those changes and actually has a algorithm that applies everywhere. Okay. All right. So this would be a good time if there are any questions. I'm not sure in this interface how to find them, but I'm sure someone will interrupt me and tell me there's a question somewhere.
Yeah, usually we do that at the end, so you can go ahead.
Okay,
and then
I'll just keep going. But it's good to get a sign of life from you, so now I know to continue. All right. So there's something other that happened recently, which is that we were very curious about these parameters that you can use to initialize your transformer to actually run the textbook algorithm, okay? And specifically, we were wondering if you initialize the model with the perfect parameters that simulate this reasoning algorithm, and you do training after initializing those parameters, what will happen? And so here I can already tell you that if you run SGD it will unlearn the correct algorithm. Right, so it will start from a set of parameters that get 100% accuracy on every possible distribution. You will train this on some specific data set for another epoch, and suddenly you will no longer run that generalizable algorithm. We don't really understand what's going on, and so this is currently being researched. But this is kind of a crazy thing to think, right? That, you know, this is all very tenuous still, but the idea that even if you were to accidentally stumble upon the right parameters that perfectly capture the reasoning function, even then, the way that we are doing the training, all our inductive biases will actually unlearn the right algorithm. Yeah, anyway, something to think about. All right, so this was a little bit of a scary message, perhaps, and maybe we can all think back to the papers we wrote with 100% test accuracy on reasoning problems and be a bit nervous about those. But I would also like to maybe provide some more positive solutions for how we can actually get symbolic reasoning to happen with LLMs. And so here we're looking at generation time. Specifically, I would like to solve questions like this one, where I need to generate text that has certain properties, like have the words frisbee, caught, and dog in this given order. It's a very simple assignment. I ask ChatGPT, and as usual, ChatGPT gets everything almost right. It has the 3 keywords in its answer, but the order is not the one that I asked for. So what is the way that we currently interact with these models? Well, we have to essentially beg them to do the right thing. We ask them, oh, that's not correct. You made a mistake here. Could you please get things in the right order? And then the next answer is even more wrong than the previous one. And so what I would like to present to you next is a system called Gelato that actually generates sentences, including these two. A frisbee is caught by a dog, which is the very obvious answer to frisbee caught dog. But then also the more creative answer of a pair of frisbee players are caught in a dogfight, which I kind of like as a creative solution from the system. Okay, so what do we need to do to achieve this goal? Okay, so currently the way that things are set up in the world of large language models is we have some prefix, the weather is could be a prefix, and then what we're given in this particular task is some constraint that says the text must contain some words, including, for example, winter, okay? Now, unfortunately, the model, the transformer model, is autoregressive, and that means that it only knows how to predict the next token given the prefix. It doesn't actually know how to look into the future and know what to do to achieve this constraint that says the text contains winter. And so if you just ask the next token distribution, what's the next word going to be, then cold or warm are roughly equally likely. But of course, if it's going to be winter, then cold is supposed to be much more likely as the next word in the sentence. There's various things that people do to somehow patch this up and to get this to work if they want to direct their generative model towards some goal. And I'm going to just take 100,000 papers and put them under this one umbrella of training some other model, Q, on a specific distribution over tasks. The distribution over tasks, this is kind of like the simple logic distribution generated by a student. You're essentially showing instances of the task you would like, training a separate model that will then try to guide somehow the distribution towards its goals. And there's many terms here that all kind of follow under this umbrella, including amortized inference encoders, mass models, and so on. And so, yeah, now you can train essentially a model that gives you the right next token given a prefix and this constraint coming from this task distribution. But of course, now given the previous part of the talk, you're also a little bit nervous about this thing, because now you know that whatever you get to work on a specific distribution over tasks is really only going to work on that specific distribution over tasks. And it's going to be susceptible to this paradox that I just showed you. Plus, you have a lot of work to do in actually training this model. So this is maybe less than ideal. Okay, and so what would be the ideal scenario? The ideal scenario would be that we can just take the distribution represented by our transformer, and we can just Bayesian condition it on this constraint alpha, and then get that indeed cold is much more likely than warm. Okay, now there's no reason mathematically why you wouldn't be able to do this. We have a distribution, we can condition the distribution, surely, right? Well, the problem here is you have to solve this task called marginalization. essentially, when I want to know what's the probability of the next token, given that I will achieve this goal of alpha, I need to sum over all the future text, and I have to see how often does this future text contain the next token, and simultaneously satisfy the constraint alpha. Okay, and so this is some kind of clairvoyance, some kind of future-looking planning that current LLMs that are autoregressive are not able to do. There are, however, a bunch of models that are able to do this type of reasoning. And so we refer to them as tractable probabilistic models, and actually many of them we refer to as probabilistic circuits. There's actually a lot of interesting research on this topic in the last 5 years, and actually the last 50 years even. But there's really a lot of machine learning based research on it very recently. And there's a bunch of distributions where we can actually just do this. I can ask these tractable probabilistic models, what's the probability that the third token is frisbee, the fifth token is dog, marginalizing out all the other tokens. I don't care about them. Okay. Now, I'm going to keep it simple for this talk, and I will just mention to you one specific tractable probabilistic model, which is a very, very old one, maybe the original one, which is the hidden Markov model from, I want to say, the 50s or 60s. Yeah. So a hidden Markov model looks like this. It basically spits out tokens in a sequence, or words in language, if you like, based on some latent variable that is changing over time. And the latent variable kind of tells you what is the type of text we're generating, what's the topic, what's the context, and so on. It's kind of like an RNN if you want. Well, so now we have an issue where we need to be able to do this marginalization I kind of vaguely alluded to. But we have actually available to us a GPT transformer, right? We have something, whatever, Llama 2 or whatever you like. So what we'll need to do is actually get a hidden Markov model from the transformer. And so in this work, we actually trained one with 4,000 hidden states, 50,000 emission tokens. So this is the vocabulary of your standard LLM from that generation. Actually, we used GPT-2 large in this work, but I'll show you some more recent work using more advanced models later. And we're just trying to essentially minimize the KL divergence between the HMM and the transformer. We're trying to get a distribution that's as close as possible to the real model, while still being a tractable probabilistic model, being an HMM here. And there's all sorts of interesting details about how you train these things on the GPU at scale and so on that I'm going to hide from you. But if you're interested in that, please check the paper. All right, so now suppose we are given this hidden Markov model that we got from our language model. Now I need to be able to compute the probability that I will achieve my goal, which is somehow important if I want to generate things that will achieve the goal. Okay, and we actually came up with an algorithm that handles constraints that look like this, or maybe more intuitively like this. We can actually compute the probability that the HMM will say swims or like swimming and lake or pool. Okay. And so these we refer to as CNF constraints. They're kind of a weird type of CNF because, of course, these words can appear anywhere in the sequence. But these types of constraints we can actually handle in time, crucially linear in the sequence length. So we have an algorithm that will compute this probability of a constraint like this, and it will only need time that is linear in the length of the English that you're generating, which is nice because we want to generate a lot of text. It's a basic dynamic programming algorithm. And if you're familiar with classical HMM dynamic programming algorithms, it's one of those things, except it's been maybe made slightly more interesting by handling these CNF constraints. And this allows us to actually solve a well-known benchmark in NLP called Common Gen. And so in Common Gen, you're actually given these keywords like snow, drive, and car, and you have to generate a sentence that has all of these keywords. But what's maybe a little bit subtle here is that keywords can have inflections. So drive could mean drives or drove, and these are all correct solutions to generating a sentence with the word drive in it. And so that's where essentially our CNF constraints come in. We have to say there's a conjunction over all the keywords, and there's a disjunction over all of the inflections of the words. So here we have to say drove, drives, drive, one of these, so that's the or, and snow, snowy, snowed, right? So you see how this ends up being a CNF constraint in what we need to generate. All right, so now we have essentially solved the problem, but we have solved the problem on a hidden Markov model, not on a large language model. Right? We have the constraints, we can handle them, we can now condition the hidden Markov model on this type of constraint, we can generate text that has the constraint. But that's not exactly what we want, right? We wanted to do this on some pre-trained large language model that is very similar to the tractable hidden Markov model, but it's not exactly the same thing. And specifically, the large language model is still better than the hidden Markov model at being grammatical, at having memorized some background knowledge, some common sense knowledge from the internet, and so on. Right. So the existing models, the llamas and the Gemini and so on, they're all very strong at certain things that the hidden Markov model is quite bad at. On the other hand, the hidden Markov model is very good at actually being goal-oriented. The hidden Markov model is able to compute the probability of achieving the constraint, of achieving the goal. So now we need some way to actually get them to work together and actually generate things that are simultaneously very grammatical, high-quality English, but also achieve the goal of generating what we want to generate. And so here's a solution for this. And we're actually going to use a very subtle little switch here in the notation. So ignore all of the red text for now. Suppose that I want to generate the next token in the large language model, PLM, given the prefix and the constraint alpha, right? This is our desired distribution to generate from, but we don't really know how to compute it. Well, if I use base rule, I can actually break this up as the next token given the prefix times the probability of satisfying the constraint given the next token and the prefix. And there's a denominator here that does not depend on the next token, so we can ignore it. Now, this term here, this factor here, is the probability of, according to the language model, of any next token given the prefix ignoring the constraint. So this is what we do all day, every day. This is what billions of dollars are invested in, is generating these next tokens. We know how to do this very well. The place where we got stuck is to generate, to compute the probability of satisfying the constraint for every next token in the language model, because we don't know how to do that. It's hard. But if we just replace the language model here by the HMM, we are actually able to compute this number. And if we assume that, at least for the sake of computing the probability of satisfying the constraint, the HMM is a very good approximation of the large language model, then this is a really fine approximation. And so this combination is called the Gelato distribution, and this is what we will be generating text from. Okay. And so essentially what will happen is the large language model and the HMM will work together. They will both generate logits for the next token, and they will be combined for the Gelato distribution to sample from. So in this experiment, we used GPT-2 large and an HMM, both with a couple 100 million parameters, and we compared to the state of the art in constrained language generation. And these are very good papers, actually. These are Knucklebest paper, NeurIPS orals, and so on. And they're all using GPT-2 large as kind of the model to generate from as a common foundation. And what we see here is that the constraint satisfaction of Gelato is 100%, which means that it always achieves the goal. And that's kind of easy to see, because if you were ever at risk of generating something that gives you zero probability of generating something that satisfies the goal, then this will be zero. And then it doesn't really matter how much the LLM likes to generate that next token. The HMM will say, no, stop it, zero probability. I'm going to erase this option. Okay. And so you have the strong guarantee that you always satisfy the constraint. And for the previous methods that learned this extra Q, if you remember from earlier, they can only really do a best effort thing. And very often they don't actually generate something that satisfies the constraint. Now, the weakness you would think of this Gelato distribution is that the HMM is not really very grammatical or a great language model, right? OpenAI is not investing in HMMs for the GPT-5. But it turns out that because we're actually having them work together, the quality of the generated text is way better using the Gelato distribution than all these previous state-of-the-art methods. And so this is kind of a best of both worlds scenario, where this neurosymbolic approach, where you combine probabilistic reasoning about logical constraints with LLMs, both gives you a hard guarantee that you do the right thing, but also just in terms of pure quality separate from the constraint, just how human evaluation judges these results, also gives you way better quality. So it's a win-win. Right? Very often you would think that to satisfy a constraint, you have to lose a little bit of quality or vice versa, but that's not the case here. I'm going to skip this part, but this is actually telling you that if you want to further fine-tune everything on a distribution over tasks, you can still do that with Gelato, and the numbers get even better. But of course, then you're susceptible to the paradox, which you may or may not care about. And again, state of the art for this setting. Okay, I think I told you most of these things. Gelato guarantees the constraint is satisfied. It does not depend on what is the task. So you don't actually have to at any point know how the system will be used while you train it. It's only at inference or generation time that you incorporate the actual constraints. The HMM is not trained knowing what the constraints will be. You can do many other things, different types of constraints in your generation. But the main conclusion here is that you can actually control this intractable deep generative model using a tractable probabilistic circuit, which in this case was a hidden Markov model. And if you like this recipe, we also have some work showing you can do this to do in-painting with diffusion models, where a probabilistic circuit can also be used to guide the generation in this conditional distribution. Okay, so this was the Gelato work, which has been out for almost a year now. And so I would like to tell you what's next. And so this is a paper that was submitted to arXiv yesterday, where we're actually building a much more advanced version of Gelato. And the idea here is that we'll have a very similar setup where we have some large language model, which now, of course, is not going to be GPT-2, but something like Llama 2 or any of the other public models that have become available. We will still distill a hidden Markov model from this LLM. So this setup is the same. But now, instead of just having these CNF constraints, we actually realized that anytime you have a DFA, so an automata representation of the goal of your generation, so anytime you have a regex, essentially, or because these are all finite generations, really, and anytime you have any kind of constraint on what you want to generate, you can turn this into a DFA. And there's actually a better version of the algorithm of the Gelato paper that just conditions the hidden Markov model on a DFA. And now this conditional distribution can again be used to guide the generation of the LLM into things that satisfy the constraint. So this is much more flexible. And so one of the applications we were looking at is essentially turning LLMs into word editors. So what if I have a piece of text and I want to replace this piece of text here by some blank, and I want to generate something new here. So normally in LLMs, they can only look at the prefix. So the way that you would do this is maybe you would put the whole thing in the prompt and you would ask replace the blank and so on. So it's kind of tedious. Now with this new system, which is called Ctrl-G, you can actually just say generate something with this prefix, with this suffix. The blank has to be something that has 25 to 30 words in it, and it must contain the key phrases alien mothership and far from over. Okay, so you can really have some really fine-grained control over how you generate things, and it's not just by begging through chat, please include this keyword, please make it shorter, please make it longer. Behind the scenes, the way this works is that all of this is turned into a very large DFA, which is then combined with the HMM to guide the generation. And so this is what it generates, and you can read this and see if you like what it does. But overall, I think it's quite impressive in how it's able to really give you exactly what you're asking for in the generation. There's some evaluations in the paper, but for now, what I'll show you here is that we compare to GPT-4 and GPT 3.5. And here we see that, of course, we get 100% constraint satisfaction for different keywords and length constraints. And so GPT-4 only 27% of the time actually generates something that satisfies the constraints that we ask for. The quality of the text is also higher according to human evaluation than what GPT-4 generates given these constraints, right? So by actually following the instructions, you actually get better text. And if you don't follow the instructions, you get more garbage. And so here, this is a case where we're actually outperforming GPT-4 on this very natural task, which is just editing text, basically. Okay, so I feel like I'm kind of running out of time, so I will spend very, very little on the last topic, but I'll try to give you the high-level pointers. And so here, the idea is that previously what we're doing is all at generation time, right? But we're never actually changing the large language model. But very often you actually want to fine-tune the large language model, and there's many applications of this, RLHF and blah blah blah. But here we're looking at more neurosymbolic ways of doing that. And specifically, we're thinking of what if I want to detoxify my language model by removing 400 toxic words from what it is allowed to generate. Okay, so this now will be our constraint, is saying, do not ever generate these really bad words. And the game has changed a little bit now, right? So rather than just maximizing the likelihood of the model given some training data, which is the usual thing, now we also have the goal of satisfying this constraint with high probability not generating these bad things. So this part is easy, the computing the likelihood. Computing the probability of not saying bad words is actually computationally hard. No one knows how to compute the probability that, let's say, Llama 2 ends a sentence with UCLA, right? So this is the whole problem, is that, from the previous part of the talk. Now, previously, the way that we fixed this is by actually having a tractable proxy model, which was the hidden Markov model, where we are able to compute this constraint. But this is not really a solution if we actually want to train the LLM itself, right? We don't want to train some separate other model. We actually need to mess with the transformer itself. And so here we're going to follow a general recipe, which you can call semantic loss, kind of a probabilistic perspective on neurosymbolic AI, where you essentially take all of the probability mass that's given to some things you don't want, and you make sure that this probability mass is gone and it's moved elsewhere. Now, the reason why we were able to do this in neurosymbolic AI previously is because very often in neurosymbolic AI, you predict many variables, but they're assumed to all be independent of each other. And then it's quite easy to essentially say, restrict the support of the distribution to only the models of alpha, the models of my constraint, the satisfying assignments. Now, the problem is we have a transformer here, which is autoregressive. And so now all of these tricks that we've developed in neurosymbolic AI, they don't really work anymore, including the Gelato trick, which is just a test time, a generation time trick. And so the basic idea of this work here, and I'm going to go really quickly over this, is to just say, well, we cannot enforce the constraint globally everywhere in the distribution. However, what we can do is pick a random point and build a tiny distribution around that point that is close to the real transformer distribution. Something that's a good approximation, but only locally around this point. And we make sure that this local approximation here is actually very tractable and can compute the probability of the constraint. And that means that we can actually enforce the constraint locally here around this point. And if we do this many times at many random different points, we will essentially generalize to enforcing the constraint globally on the whole distribution. This is the loss function we use. It's called the pseudo-semantic loss function. It looks very complicated. I'll try to give you the intuition for every term. So the minus log here means we're going to compute a probability and turn it into a loss function. This basically means we want the probability of something to become 100%, at which point the loss will be 0. The probability that we would like to become 100% is this thing here. It involves this expectation here, which is pick a random point in the distribution, which is around where we will enforce the constraint. Then around that point, we will build a little tractable distribution, which is this simple product in every dimension. And so this is a very weird thing, but let me just show you what it means on a language model. It means that I picked a point, I saw a dog today. That's my random point. I want a tractable distribution around it. And what this means is I will independently alter every dimension. I will consider every word to be a different word, okay? While keeping everything else fixed. And so now I need to compute all these probabilities. And then I will pretend that when I'm given a new sentence, I can essentially multiply all these probabilities that I have pre-computed here by independently changing every dimension. And then you get these little inconsistencies. For example, the probability of today is conditioned on dog instead of mouse because we've changed mouse here. But we're just going to pretend like this is okay. And this should be okay, at least locally around the point. Okay, so it's a silly local approximation. And then what we'll do is around this silly local approximation, we will compute the probability of the constraint by summing over all satisfying assignments, all of the text that does not contain the bad words, if you want. All right, so that's our loss function. And computing this thing here turns out to be quite easy. Here we have the existing neurosymbolic AI tools that do this for us. Okay, so we can take off-the-shelf solutions for doing this practically. Okay, this is basically telling us it's a good approximation. It has some uncertainty, but it's close to the transformer distribution. You can evaluate this on the standard neurosymbolic benchmarks like Sudoku, puzzle solving, or finding shortest paths in Warcraft, and then you get a very significant boost in performance because of using a autoregressive distribution as the output layer of your neural network, which gives you a significant improvement. But our real goal is to actually tell the people in NLP that neurosymbolic techniques are very useful for things like detoxifying language models. And that's exactly what we did here. So we took GPT-2, and then it actually generates a lot of toxic text. So this is how toxic it is, maximally over some generations. And this is the probability of toxic generations. There's toxic prompts and non-toxic prompts. And of course, the toxic prompts tend to generate very often toxic text. How is toxic defined here? Toxic is not defined as this constraint being satisfied. Toxic here actually means something more general, which is Google's API for toxicity classification says that this is toxic. Okay? So even though we're just looking at constraining the model to not generate certain really bad words, the way that we evaluate the model is in a more general notion of toxicity. Like we don't want even subtle toxicity that's not literally these bad words. Okay, so a few things you can do is, with the state-of-the-art methods, you can kind of filter the data set and so on, and you can kind of reduce the amount of toxicity without ruining the quality of the text too much, okay? And then if we use our pseudo-semantic loss, we actually see that we reduce the toxicity probability and a degree of toxicity further, while also not ruining the quality of the text too much. You can then further say, I want to do word banning. I want to literally stop the model from generating anything in this list of 400 toxic words. And then you get even less toxicity. And you actually get the state of the art compared to this previous method. And so the summary here is that, yeah, these neurosymbolic methods that do symbolic reasoning at training time as part of the loss function are actually able to get really strong results in even something that doesn't really seem like a neurosymbolic task, right? Toxicity is not something that is defined in terms of bad words. It's something more subtle, right? Toxic text can be, very, semantically even hard to tell that it's toxic. But, even by just having this lexical constraint of don't say these bad words, it's able to generalize to not going into this toxic mode of the distribution, essentially. Okay. Summary of the talk. There's a paradox when you try to do learning and reasoning just from data. That's a bit scary, but you can build interesting architectures that combine reasoning algorithms that are robust with trained models at generation time. But you can also then do at training time a combination of the two that actually gives you very robust models and you can teach the model to do the right thing, essentially. And of course, the solutions are all revolving around some combination of taking logic, making it differentiable by doing probabilistic reasoning about logic, and then making those differentiable algorithms actually be layers in PyTorch and part of your deep learning architectures. All right, so that's the end of my talk, and I should thank all the folks who worked on these topics, and especially Honghwa, Karim, and Meiwa, who are the lead authors on the work that I presented. Thanks for your attention.
So great talk. We already have, I don't know, Luciano, if you want to lead the Q&A.
You're on mute, Luciano.
You're muted. Well, I could start by reading. We have a question from the chat. Okay, now Luciano, you can. Okay, please
Sorry,
go ahead, Luciano.
I was muted. I was looking for the picture for the windows of the. So can I start with a question, Guy?
Please go ahead.
Okay, so I'm interested in the second topic on the introduction of the hidden Markov model to somehow guide the or filter. I don't know. It's a kind of composition, say, of what is returned by the large language model. So as I understand, but I might be wrong, your big CNF that you provide, you give for every word, you give the alternative, the different, basically for every lemma, you give all the different possibilities. I remember this big disjunction that you put there. Okay, yes. So now, does it mean that you have to kind of write this very big disjunction for all the possible variation of one word? So you have to.
I mean, yes, I see your question. So how do we know that drive, drives, and drove are all inflections of the same word?
There could be many of these.
Yes,
right?
yes. So there's some agreed upon standard apparently in the NLP community where you have tools that tell you these are all the inflections of this particular word. So it's a little bit subjective, but in terms of benchmarking, people essentially have APIs to generate inflections. Yeah.
But wouldn't it better to have something like, because the LLM, propose the word, and then you simply have to check if the proposed word is an inflection of one of the given word.
Right.
Better to do this when the LLM proposes the word.
Yeah, so that's a good point. However, we're not actually just looking at, let me go to, right? So we don't really care what the LLM proposes. We have to actually look at the constraint being satisfied in the future. So we have to think about everything that the LLM might propose later on in the generation and all of the possible inflections that might all satisfy the constraint, right? So it's not enough to just look myopically at the next token because then this wouldn't work. You have to kind of see if I'm going to say now cold, then later it's more likely that I will generate winter, right? And all the inflections of winter. So it's not as simple as looking at one specific token being generated. You have to look at all possible generations.
Okay.
Yeah, good question.
Then, thank you very much. And then I have another question that I will leave for the audience. Okay, so you do a great job for the sequential data like text. Any idea of how this method could work on other type of data like images or even say multimodal large language models?
So you mean specifically the Gelato model?
For example,
yeah, right. So for the Gelato model, there is a purely image version of this, which is called Tiramisu, which appeared at iClear, I guess a month ago. And so the idea there is that we don't have a transformer, but we have a diffusion model. And so diffusion models are also very bad at conditioning the generation on patches. They kind of have weird artifacts. They kind of not get globally consistent in painting of the image. And so there we actually show that if you take a tractable model similar to the HMM, but obviously not an HMM because it's for images, you take a tractable model and you condition it on these patches, you compute the posterior distribution, and then you use that to guide the diffusion models, you get also state-of-the-art kind of zero-shot in painting with diffusion models. And so, yeah, so these ideas definitely generalize to any kind of modality, but not all the, not all the papers have been written, I guess, on all these, yeah, ways of applying the idea. Um,
Okay, thank you very much. So, Antonio, can I ask you to drive the question online because I have some difficulty in seeing them.
Okay, yes. So I can read there are a couple of questions. One by Martin Wells that says, I'm reading. So the concept of system one and system two from Kahneman suggests that logic is treated in system two independently. So why do we now want to include everything in system one, which is the LLMs, say in this case? This is the first question.
yeah, that's an interesting question. So I don't know much about psychology and so on, but I do remember Kahneman maybe 4 years ago at some AI conference saying, "Oh, you AI people, the whole system one, system two thing, the way you present it is maybe not as simple. It's more complicated than how you present it." So I don't really know what the real thing, but what the real kind of details are of that theory. But in the end, I don't think it really matters. I mean, what do we call system one and two here? I could say the HMM is system two. It's intervening on system one, the LLM. But this is just, I would say, this is a sales pitch for me. I don't really have strong opinions here. Yeah. I also don't think historically in AI that it matters all too much what the human brain does. But I don't want to offend too much the people. I think it's a good inspiration, but I think you can cross fertilize, but I don't think you put constraints. I don't think one field should put constraints on the other in how it should do things. That doesn't really, that doesn't strike me as a fruitful way of doing things. But yeah, I don't know. Maybe I have a strange opinion there.
Okay, there are other questions. Okay, for example, I'm reading. Okay, last one. Okay, by Amanda Hicks. The example motivating the paradox focuses on formal reasoning. The solution focus on reasoning about meaning. Do these techniques help with formal reasoning also?
Yes. So part of this new paper that's just posted to archive yesterday and will appear, I guess, later this week is we ran on some, I think it's a math benchmark, where essentially we put the constraint that in the chain of thought, you have to use all the numbers given to you in the assignment. So some very simple lexical constraint that actually helps also with the type of reasoning in the same style as the first part of the talk. So obviously there's a gap, right? Someone else asked in the chat, like, a lot of constraints that we want, like we want, truthful, we want no hallucination, we want correct reasoning, we want non-toxic. These are all things that don't have a logical definition, right? These are very subjective in some way. And so I think part of the problem here is we have to, when we use symbolic algorithms, we have to make them formal, meaning we have to say things like toxicity is now reduced to this simpler concept of don't say 400 bad words. But I think still this is a very useful thing, because if you do this and you do a good job at the symbolic constraint, you actually end up doing very well at the more subjective constraint that is not captured symbolically or formally very well. And so the same with reasoning is I cannot, unless I actually write the algorithm down, I cannot force the transformer to do the right thing, but at least I can give certain symbolic feedback and certain lexical constraints that will improve its performance in terms of this metric. So I think that's where we're going in future.
Yeah, this also answer to one of the questions by Wheeler Room about this kind of issues. There is another one which asks about what type of tractable model is used in tiramisu instead of an HMM.
Yeah, that's a good question. So I gave this picture here somewhere of probabilistic circuits, right? So probabilistic circuits is this general kind of computation graph of essentially all deep generative models that allow you to compute a marginal probability efficiently. And so hidden Markov models are in some form probabilistic circuits. They're just doing layers of sums and products. But there's many other architectures of layers of sums and products that essentially have this property. And for this tiramisu model, we have an image probabilistic circuit that's been specially built for images. There's been a lot of research on improving tractable generative models for images recently. And I encourage you to check it out. Yeah, so if you search for probabilistic circuits for, let's say, ImageNet 32, ImageNet 64, you get some interesting recent architectures. And they're not as well known as HMMs, but they're very interesting. Yeah.
Okay. I
Um,
don't see.
I have a question, because I see there is no other question online. Is it possible?
I don't see any other question. Then I have one, but after
No, no,
the
you go on, tell me.
Okay, so it's just, let's say, a question about, it's related probably also to the first question that you had, because about, let's say, cognition and, let's say, relation with human cognition. So in one of your slides, you have, let's say, compared the result that you obtained with a measure that you have called quality, which is a human evaluation, right? So I wanted to ask you a little bit about how did you set up this human evaluation? Because it means that, again, these systems are used in with humans in some cases, right? So that's why
Right.
it is important also to take into account this kind of, let's say, aspects coming from cognitive theories. But the evaluation, for example, in cognitive science is really important. So I've seen many times, let's say, reported evaluation in the AI talking about, let's say, human level performances or superhuman level performances that in cognitive science would have been never published because these are not controlled experiments and so on and so forth. So I was curious
Right.
about how did you set up this human evaluation on the aspect of quality?
Yeah, that's a good point. And I should know more of those details. They're definitely in the paper. But essentially, what we did is we used each of these four models to generate solutions to the insertion task of, like, essentially it's this one here, right? We basically gave these different tasks to the models. We generated the output, and once you see the output, you don't really know anymore what were the constraints, what were the keywords, what were the prefix and suffix, and you just ask people, how do you rate the quality of this text? And I think there's various metrics we used. I don't know. So there's actually a human evaluation of Gelato, and there's also one of this new system, Ctrl-G, and there might be subtle differences there, but essentially they're mechanical Turk workers being asked,
Okay.
how do you rate the quality of this text?
Okay.
And,
Okay. It's
yeah,
a
if you have
rating.
feedback on how to do better human evaluation, feel free to send it, because I think this is traditionally not the strength of the machine learning community, but
Yeah.
it's kind of
Yeah.
important these days. Yeah.
Oh, yeah, it's very important. Okay, yes, I will. So, I mean, if I understood correctly, it's a sort of, let's say, crowdsourcing evaluation where you have
Yes.
rating annotators that provide some ratings
Yes.
on
And there's some exam that tests whether the annotators are capable of doing a good judgment and so on. Yeah.
Okay. Okay. Thank you. There is probably Luciano.
Yes, I have a question about the final state machine that you use instead of to impose constraint on these Ctrl-G stuff.
Uh-huh.
I mean, I when I see DFA, I think to temporal logic. Is it because you are allowed to put some, say, temporal constraints on on order, on the appearance of the word, or am I, it's the wrong intuition?
Yeah, so I think most of the intuitions people have about DFA and regular languages and etc. Most of these intuitions don't carry over here because all of these generations are limited in length, and so therefore anything can be represented by the weakest languages, because these are all essentially a DFA restricted to you generate 20 tokens or 1,000 tokens or whatever. And so, yeah, you could write in a very expressive logic whatever you want, but since you're going to actually limit the length of the sequence, it's all just going to be reusable to a simple DFA or yeah. Does that make sense?
Yes. Well, I was essentially asking if you can impose order on
Oh yeah,
generating.
yeah, for sure. For example, the prefix and the suffix really means this, this happens before that, right? Okay, the prefix is already given in the prompt, so that's kind of cheating. But yeah, you can easily say, actually, the paper has some examples of this where you say, I want this keyword before that keyword before that keyword, just like the first example of the frisbee caught dog. Yeah, so that's very easy to do by just chaining together the DFAs for the individual constraints. Right, so you have the standard constructions for how to combine compositionally the DFAs. And
Yeah, it was very
yeah,
interesting. I mean, this thing.
yeah, yeah, yeah.
Thank
But
you.
if your question is more about like what can we express with a DFA, then the answer is everything, because this is all for finite for bounded sequences.
Yeah.
Okay, so I don't see other questions. Thank you for the really great talk, Guy. So it was a pleasure for us to have you. I will just spend and invite Floriana also to join me. A few words about this series of seminar. I think we really had a great lineup of speakers. Marco Gori, Elena Simper, and now Guy van der Broek, and we are very happy about what we did. We look forward, right, Floriana. I hope to continue this collaboration with AI SB in the fall. I don't know if you want to.
Yes, definitely. I think it was a successful synergy. And I think, as you said, the three speakers were outstanding, very interesting, and we saw from the YouTube channel that there was a lot of interest from the audience. So yeah, I mean, looking forward for the autumn at this point, a series of seminars with AI.
Okay, so that's great. Thank you, everyone. So see you in the fall with another series of great seminars. Enjoy your summer, and thank you again, Guy, for this great talk. Bye.
Thank you very much. Bye bye.